So having spent some time talking about health data, I want to talk about the other side of the epidemiology equation, which is exposure. So I want to begin by defining the difference between dose and exposure, because people often mix them up. So dose you can think of as the amount of a substance that actually enters the body as a consequence of some mode of absorption, which is very often ingestion, inhalation, or skin absorption. On the other hand, exposure is usually the concentration and duration of a substance, often a chemical, that is in direct contact with the external surfaces of a person. So it may be the skin, maybe the respiratory tract, or maybe the gastrointestinal tract of a person. And exposure assessment is the process of assessing people's exposure, which we're always trying to do in epidemiology. So when I talk about exposure, I'm talking about just about everything you can think of. This is a list of chemicals, microorganisms, radiation, smoking history, noise, and so on. Even genotype, a person's genotype can be thought of as an exposure that they have. So much of what we study is external to the person, but it can be something internal, such as the genotype. So we're also interested very much in routes of exposure. So how does the thing that we're exposed to actually enter the body? And commonly we study inhalation, ingestion, and dermal exposure, or skin absorption. In special circumstances, we might be interested in injection of something into the body. There is also the possibility of oral exposure through the ear, or ocular exposure through the eye, and then there are other things like radiation, vibration, which don't quite fit into any of those categories very neatly. It's possible to think of a person. This is a kind of a schematic person, and in order to illustrate exposure. So the exposure is what is in this area which is outside the surface of the person. So it's what actually passes through the gastrointestinal tract. It's what goes into the lungs, but is not actually absorbed into the body. Once it gets absorbed into the body, it becomes dose. So anything in here is dose. When we talk about arthropod-borne viruses and other diseases, that's basically injected through the skin, and then of course you have ocular exposure here. So this is simply to try and more clearly illustrate the distinction between dose and exposure. Anything on this outer surface is exposure, anything that gets in is dose. So there's a whole discipline of exposure assessment, and experts in exposure assessment commonly work closely with epidemiologists, and there are even joint meetings between the International Society for Environmental Epidemiology, the meeting of which I try and attend every year, and the International Society for Exposure Assessment, which is basically people from many of these disciplines, and they are focused on measuring as accurately as possible people's exposure, particularly to chemicals and microorganisms and radiation and so forth. And the two general fields work together very closely. So why do we care about accurate exposure assessment? Well, several reasons, but epidemiologists are particularly interested in distinguishing one person in a study from another in terms of exposure. If everybody was identical in terms of exposure, then we wouldn't be able to distinguish any relationships between exposure and health outcomes. So we really need to accurately be able to determine who is highly exposed, who is low exposed, and in between. So it's absolutely critical to us for our studies, or we wouldn't show anything. so that's the general. We're trying to avoid the problem of exposure misclassification. We're going to talk about that in more detail in a future talk. And the other thing is related to the first point is that very often in our studies we are interested in defining the relationship between exposure and disease in order to establish valid exposure standards, maximum exposures, permissible exposures, which may apply to food or water or air. So those are the reasons we really do rely on accurate exposure assessment very much. So it sounds straightforward, but really exposure assessment can be really difficult, and particularly for epidemiologists in today's world, because many people would say that epidemiologically the so-called low-hanging fruit have been picked off. In other words, the exposures which produce very high relative risk estimates, such as smoking, for example, which may produce relative risk estimates of 10 to 20, say, those ones which are more obvious, easier to detect, easier to find the relationships, many people believe that most of those have already been discovered, and so the focus these days is more on identifying risk factors which have a smaller effect on people. On the other hand, they may be affecting billions of people. Billions of people may be exposed, so they may be very important. It's not necessarily the case that all of the very strong risk factors have been found, but probably many of them have been. So a second reason is that which makes it difficult is that very often when we're interested in non-communicable disease causes, the critical exposures may have occurred many years ago, maybe decades ago. We certainly know that to be the case with cancer, because there's a long latent period, maybe decades, and so it makes it very difficult to figure out to figure out causal relationships, because you really have to connect up past exposures with current diseases. So that's difficult. And then it may be that the level of exposure has varied on a daily or a minute-by-minute basis, and so we'll illustrate that with this example here, where we have a person that's been followed over the course of a day, and their carbon monoxide exposure has been measured. And you can see that over the course of the day, and they drive to work, and they're walking and smoking and so on, and cooking. Under certain times of the day, the exposure is very high, other times it's very low. So it's very difficult to actually sort of integrate exposures like this over time. So you can put a personal carbon monoxide monitor on a person, and you can measure it maybe for a day or two, but it's very hard to do that over a longer period of time. Very hard. So you usually have to make a lot of assumptions. And when something like this has happened in the past, it's even more difficult. So, and then fourthly, the agent which caused the disease may have left no identifiable trace, and this is very likely to be the case for anything that occurred decades ago. There are some chemicals which accumulate in the body, but there are a limited number of those, and they are still excreted. So the concentrations that were in the body years ago, they're not reflected by today's levels. So it makes it difficult. Another reason is that people often don't know they were exposed, and so even if you interview them, you won't be able to find that out. You might be able to find out where they were, where they lived, where they worked, that sort of thing, but they don't actually know what they were exposed to, and so you may have to find other ways of trying to recreate that exposure based on such things as knowledge of what industry they worked in, or data on the water supply in the town where they lived at the time, if it exists. But unfortunately, there is a lack of historical exposure records in most situations. So occasionally we can find historical measurements of contaminants in food, or contaminants in the water supply, or even in the air, but in most situations that sort of information is not available to us. So all of this combines to make exposure assessment, particularly over the longer term, extremely difficult, but we do our best. Complicating the picture is the fact that exposure just doesn't come from one source necessarily. And so this is a schematic which shows a human here and sources of lead exposure. So there are various sources. It may come in our food. Or it may be inhaled. And certainly inhalation of lead was a big thing in the days when gasoline was leaded. But still there may be industrial facilities which are emitting lead even today. Some of it may get into the water supply, and we may ingest it. So, but then there is a complex movement of lead in the environment, and gets into the soil, particularly lead from old paints on old houses, and young children may ingest it, and there's this habit of eating non-food objects, sometimes referred to as pica or pica, however you prefer to pronounce it. So that's an additional source of exposure for young children. So we can see that to actually get a good idea of the extent to which people are exposed, we need really to be able to try and put together this picture, kind of identify all the various sources and how lead is moving between the various sources. So it can be very complex. We use multiple sources of exposure data, and one which we use a lot in epidemiology is questionnaires. And so I'm going to be spending some time, my next 3 talks are going to be about questionnaires, how to put together questionnaires and administering them and ensuring data quality. But there are other methods. So we can have diaries. We can ask people, for example, to record the foods that they eat over a period of time. Though people's tolerance for doing that for a long period of time is pretty limited. We can use medical records, particularly the medicines that people were prescribed, which doesn't mean to say that they actually took those medicines, but anyway, but at least we can get the information on the medicines prescribed. There may be ambient air pollution monitoring data that we can use under certain circumstances. And there may be data from what we would call point sources. So a point source is a particular focused source of exposure, and say a factory chimney would be thought of as a point source of exposure. And it's possible to model, using meteorological data, emissions coming out of factory chimneys, and using dispersion models can calculate the concentrations at different points around the chimney, say. There may be water supply and monitoring data. There are some requirements for regular monitoring of public water supplies, and those data can be available through health departments. And then there may have been some food sampling or nutritional survey data collected, which may be available and may be useful to us. I'm going to talk a little bit more about biomarker measurements coming up very shortly, because they are useful to some degree, but certainly they have gone through a phase of popularity, I would say. Dust and soil analyses, we may have some information on dust and soil from homes, may give us some idea of what infants and young children are exposed to. And we may be able to do direct personal measurements, and I just showed you a graph of direct personal measurements of carbon monoxide. We can attach personal samplers to people, and if they're not too obtrusive, they may be willing to carry them around for a few days and measure the the concentrations of various chemicals that they are exposed to over that time. And finally in this list, we can get information on workplaces, so just knowing where a person worked may give us some information on what they're exposed to. So these are sources that we may use depending on the circumstances, what we're investigating. So there's no single source of exposure data, and inevitably our information on exposures is pretty incomplete. However, we do our best. But I'm going to talk a little bit more about biomarkers, and then we'll move on to talking about questionnaires. So, what's a biomarker? Well, it's just a very short term for biological marker, and really it's usually some cellular or chemical indicator of exposure. So it's actually more of a measure of dose. And we can define three types of biomarkers: the biomarkers of exposure, biomarkers of susceptibility, and biomarkers of biological response. So in the next schematic gives you some idea, trying to sort of break those three types of biomarker down, show you how they relate to each other. So looking at the top, this is traditional epidemiology here. So we have an exposure, whatever it may be, some chemical perhaps, and then we have a disease, some health outcome. And then we are interested in studying the relationship. But what actually happens between the exposure and the disease is kind of a black box, as shown here. So molecular epidemiology attempts to get into this black box and elucidate what happens. So here over on the left-hand side we have exposure, and right on the other side we have some markers of disease, clinical disease. So molecular epidemiology, we may take, for example, blood samples and get some measure of internal dose. We may be able to get tissue samples, particular tissues, and get some measure of what we call the biologically effective dose. In other words, so what we detect in the blood or the urine may be some indication of the dose which the body received, but it may be more important to know what the dose was at a particular target organ, such as the kidneys or the liver or whatever. So it may be possible sometimes to get a measure of the concentration in one of those target organs. But anyway, the biologically effective dose may lead on to some early biological effect, which may alter the structure or function of a particular organ, and that can progress to actually clinically detectable disease, which may have some prognostic significance for the future. So at each of these stages, starting with the internal dose, biologically effective dose, it may be possible to get some biomarkers. So moving from biomarkers of dose or markers of exposure through markers of effect or disease. So, and then there's a kind of a transition over here where the distinction may be a little hazy. Then we have markers of susceptibility. So these may be various genetic variants, for example, different genes, different alleles affecting the absorption, may influence absorption, may influence how a chemical is metabolized in the body, it may influence the impact that a chemical has in the body in these various other markers of susceptibility. So for the most part, markers of susceptibility are related to people's genotype. So that's how markers of exposure, markers of disease, and markers of susceptibility more or less fit together in this black box here. So some biomarkers of exposure, just so to give you some sense of this, because I'm mainly going to be talking about biomarkers of exposure here, because this talk is on exposure. So if we're interested in people's exposure to tobacco smoke, we don't usually measure nicotine because it has a fairly short half-life in the body of maybe an hour or two. But cotinine, which it's metabolized to, is a much longer lived chemical in the body, and so it may be present from 17 to 19 hours, say. So we might measure cotinine in saliva. And there's a class of chemicals known as dioxins, some of which are extremely toxic, and they're all fat soluble. So we may measure them in breast milk. So we may be interested both in the exposure of infants, but we may also be interested in dioxins in breast milk as a marker of general population exposure, since breast milk contains quite a lot of fat, and it can be obtained non-invasively. In other words, we don't need to stick a needle into somebody. Samples of breast milk have been used very usefully to get a sense of the level of dioxin exposure in different populations. Lead in blood, traditionally lead has been measured in blood, and a lot is known about that. It can be related to various health effects, particularly impacts on cognitive function in children. Alcohol in exhaled air, the basis for the breathalyzer test. So that's, although most of us don't think of it that way, that is actually a biomarker. Arsenic in urine. So I used to do research on inorganic arsenic in drinking water, and particularly in relation to whether or not it caused cancer. And so one way, the main way we had of estimating people's exposure to arsenic for drinking water was by getting urine samples, and that gives us a fairly good measure of arsenic exposure. Carboxyhemoglobin in blood. So this is can be used as a measure of exposure to exhaust gases or smoke, or tobacco smoke included. As this is a combination of carbon monoxide and hemoglobin in the blood. Benzoapyrene adduct. So benzoapyrene is a polycyclic aromatic hydrocarbon, a chemical, one of a class of chemicals known to cause cancer in humans, and these combine with DNA. So by by extracting DNA from cells and measuring the number of DNA adducts, the combination of benzoapyrene with the DNA, it gives us some sense of the extent to which people were exposed to these chemicals, the polycyclic aromatic hydrocarbons. And then there's a fumigant called methyl bromide. This reacts with hemoglobin, so it forms these methyl adducts with hemoglobin, and so by measuring the methyl adducts in the hemoglobin, you can get some sense of the extent to which people have been exposed to that fumigant methyl bromide. So as I've just illustrated in many ways, the biomarker exposure may be the actual chemical that people are exposed to, and an example of that would be lead in blood, but it may be a metabolite of the exposure, in other words, a metabolic product in the body, and the example I just used was cotinine from the nicotine, because we don't measure the original nicotine. An adduct, we talked about a couple of adducts, or DNA and hemoglobin, or it may be an altered level of enzyme activity, and one example of that would be the effect on the enzyme acetylcholinesterase, which is in the blood and has some sort of normal level in most people, and by taking a baseline level and then measuring pesticide sprayers, particularly those who spray organophosphate pesticides such as, for example, malathion or parathion, and those chemicals, those organophosphate pesticides, actually reduce the level. They inhibit the acetylcholinesterase enzyme, and so by measuring the change in the activity of the enzyme from, say, a baseline level, maybe at the beginning of a spraying season, one can see to what extent a pesticide sprayer has actually been exposed to these pesticides during the course of their work. And this is moving on more towards measures of biological effect. There may be, we may measure measures of damage, and these can be chromosomal abnormalities or changes in lung function. So these would be regarded as biomarkers, but more biomarkers of effect than biomarkers of exposure, but they may be reflecting some level of exposure that's occurred. So where do we get our biomarkers from? So this schematic here basically shows the tissues that are available to us. So we can get sweat or exfoliated skin cells. We may get exhaled air, causes blood. Blood, we often try and avoid that because many people don't like to have blood samples taken, and in fact if you ask people to participate in an epidemiology study, you will have a higher participation rate if you a higher non-participation rate if you ask people to provide a blood sample, because many people simply just don't like it. So if we can collect other biological media such as hair samples or urine samples, which don't need to be collected invasively. Feces, not necessarily very popular, but at least it can be collected non-invasively. And saliva. Saliva's very popular these days, particularly for getting DNA samples. So biomarkers have some advantages and some limitations. First of all, they do provide some objective measures of the individual dose. This is talking about the advantages. And then and you can think of them as integrating exposure over different routes of intake. So for example, lead. If we get lead from our food and we inhale it and we get it in the water, by getting a blood lead sample, it's actually integrating exposure over all those different routes of intake. It can integrate fluctuating exposure levels. So as an example of that, I showed you earlier on how a person over the course of a day is exposed to extremely varying levels of carbon monoxide. Now, if you were to measure the carbon monoxide level, or carbomonoxyhemoglobin level in the blood, then this will give you an integrated level over the course of a certain time period, so you wouldn't have to be using a personal exposure monitor to look at those fluctuations that they're exposed to. Now sometimes we can obtain, if we're interested in the time pattern of exposure, how exposure changed over the course of say weeks or months, we can sometimes do that by collecting hair or nail samples, so fingernail samples that is, or toenails, and that's because as hair grows it incorporates some chemicals into it, like lead or mercury. The hair grows out from the root, it's incorporated into it, and just by measuring the distance of by segmenting a hair sample, or even so fingernails or toenails, you can actually calculate when people were actually exposed to certain chemicals, but it only applies to a relatively small number of chemicals. Now, biomarkers, despite their attractiveness and the fact that they do have some advantages, they also have some limitations which really severely restrict their usefulness. And one of those is that they mostly reflect only very recent exposures. There is a small class of chemicals where there is some level of accumulation over the course of years, but they're relatively small. I mean, some heavy metals like lead, mercury, or lead in particular, may accumulate over time, although there is excretion going on all the time, so it's not like just a progressive increase on and on. In some fat-soluble chemicals, such as the dioxins and also some of the older pesticides like DDT, dieldrin, and some other chemicals like polychlorinated biphenyls and some of the recent flame retardants will accumulate over time. So not just only recent exposures, but for the most part they really only reflect recent exposures. And so if you are interested in what happened to people years and years ago, then really biomarkers are of very little use, particularly if people's exposures have been changing over time. If they've had a kind of constant exposure situation, then it might be assumed that a measurement of their current exposure is reflective of what they've had in the past, but very often that's not the case. People's exposure has changed over time. A second limitation is that they may require invasive techniques. So if you're going to get a tissue sample, then that's very off-putting for most people. So many people will not be willing to participate, and certainly if you, even if you're getting, as I said, a blood sample, that will reduce participation rates in any epidemiology study. So if you can avoid blood, then do so. The third limitation is they can be really expensive. So we're often talking about extremely low levels of chemicals to be found in the body, and so it needs very sophisticated and expensive analytic methods. So the expense can be quite high. For example, some of the dioxin measurements, it could be $1,000 a sample, for example, of that order anyway. Finally, the timing, we have to be very careful with the timing of our sampling relative to exposure, and let me illustrate that with biomarkers of smoking. So I already mentioned cotinine, which has about a 19-hour half-life in the body. But if we wanted to look at nicotine, when people are directly exposed to from cigarettes, then it has a 2-hour half-life. So we really have to move very fast if we are going to measure nicotine, and that's often very inconvenient. And by half-life, I mean, what is the time that it takes for half of the amount of it in the body to be excreted, or to disappear, to be metabolized in the case of nicotine. Carboxyhemoglobin, produced by cigarettes, the carbon monoxide, so that has a bit of a longer half-life than nicotine. So 3 or 4 hours, it'll remain attached to hemoglobin, so you can measure the carboxyhemoglobin in the red blood cells. Cotinine is a bit better than that, the 19-hour half-life, which is very convenient for many people. So cotinine is often used and it's also very specific to smoking, because nicotine is a very specific biomarker of smoking, and cotinine is a specific indicator of the previous presence of nicotine. So it has that nice quality of being very specific, whereas carbon monoxide can come from many sources. It's not just specific to cigarettes. Thiocyanate, not just specific to cigarettes. It can come from some vegetables, for example. So, but it can be an indicator of smoking across a period of a few weeks. So it can integrate over a period of a few weeks. And then finally, 4-amino biphenyl hemoglobin adducts. So they stick around the body for quite a long time. And so if you're really interested in a person's exposure to tobacco smoke over several months, then use of 4-amino biphenyl hemoglobin adducts might be appropriate. So the point there is really you have to pick your biomarker depending on the time frame of the exposure that you're interested in.